review the very useful, certain useful formulas in Laplace transform, and then that will be easier allow us to do something. So this page here showing is we call the shifting theory, and there's a few different types of the shifting theory. And here, let me review the first one, and this one, let me show the top here. So basically, this shifting theory, this is, let me pick up the two examples here. So in Laplace transform tables, we know the sine of AT in the Laplace transform is this, cosine is this, okay? And so here is one example here. And most of the time in control systems, we will see the individual functions, for example, cosine t, will pre-multiply with certain exponent functions. So for this kind of case, when you have this kind of case want to transform, then the Laplace transform can be treated like this. And look at here. So let me use the cosine and bt. Okay. So first one from the Laplace transform tables, and we know this one corresponding is s squared plus b squared s. Okay. So you check out the form from the table, and you know if that function multiplied with exponent function like this, then its Laplace transform is this. You multiply with that form, right? Because this is generic function, they multiply with the exponent. And for this is this. You cover up this one mentally, and you write out the generic form. So that is s squared plus b squared. Okay, and once you have this as the platform, then you do the replacement. S is replaced by s minus a plus minus a here. Okay. Okay, good. So that means here the transform will be s minus a and s minus a squared plus b squared. Okay? And you see I do the replacement is this one. I replace these letters with this one. See? Okay? We can do a little bit more exercise. So for example, sine t, sine bt, and this one multiply with at. Okay, so the same thing, and we look up the tables, and for sine bt, we know that is s squared plus b squared times what? B, right? Okay, so that is a platform for sine, and right now this pre-multiply with exponent. Then here the s simply replaced by s minus a. So this one will be equal to b s minus a squared plus b squared. Okay? We can do a little bit more exercise. So say, let me make up one. So say t times e 3t. How about this? Okay, so for this one, the Laplace transform is this. We cover up this for this time being, and look at what is the template for this one. So for the Laplace transform of that is t. Okay, sorry, my typo. That should be exponent multiplied with this one. Okay. So cover up this. The Laplace transform for this one is s squared, right? Okay, and then you replace s by s minus 3. Okay, so that one will be equal to s minus 3 squared. One there. Any questions? Should be very straightforward, right? And now we do a little bit different exercise. So we can exercise this one. So we do this one, 4, look at here, 4 divided by s squared plus 4s plus 20. So right now we want to find the plot transform, inverse of the plot transform. So we try to simplify is this. You have to simplify, not to simplify, you have to arrange the terms into a certain template like this or this in the way we can have this something can refer to. Okay, so for example, for this case, denominators you must arrange, because this one is a second degree polynomial, we arrange into either this. We do it, okay? So, so the hint is this, the s squared plus 4s, and I want to make a complete term like this one. Okay, how to do it? You know, s squared plus 2a, 2 alpha s plus alpha squared is s plus alpha squared, right? To make it, so 4 equal to 2 alpha, alpha equal to 2. So here you need to make up is alpha squared, 2 squared, right? That is 4. Okay, and now originally is 20, so 4 plus something equal to 20, 16. So that this one will give us is this form, s plus 2 squared. Got it? And then remaining is 16. You make it up by arranging the things. Okay, so we keep writing here. So let me rearrange again. Here we're showing is the certain square. So why not we simply convert one more time to the 4 square? It will be easier for us. Okay, and right now you can see denominator has appeared in the form we know, and numerator is a constant. So here is s, this is constant. So basically you should expect once it transformed, inverse transform, it must be in sign. Because sine has been with the numerator is constant. Cosine always become with s multiplied with certain coefficients. Okay? Okay, so now we continue. So here, how to do this? Taking up this one. So you can see how to do that one. So right now for this one, b squared b, and this is b equal to 4. Exactly this 4 is making this one. Good. I don't know if it will be easier for you to modify. Say, can I make it? So say if this is 3 rather than 4, let me make a little bit more general case. Okay, we exercise this example. If this will be 3. Okay, then you have to make it up. So in this way, you have to do it is 3. If you want to make the minus, because here in our template it's as 2 squared plus 4 squared. This is b, and in our template of the formula, this should be 4. Okay, but this is 3. So basically, you have to multiply with this one. Because this one you cancel 3 over 4 multiplied by 4 equal to 3. You make it up and then rescale back to the original. Okay? Good. Okay. So now we come to the thing. So right now we have this 4 and s plus 2 squared plus 4 squared. And how to do this? Again, if you look at this one, if you think of this one. Again, you know this one is numerator is constant, and this is something as square plus 4 square. You treat this one as the something as, then you know this pattern. So say if this is with this kind of integrated, you know this one should be corresponding to sine 14, right? If this is only s squared plus this one, then that should be this. But here we already have a replacement s plus 2. So using this replacement, we do the backward process. This one corresponding is minus 2d. Okay? This exercise, we're doing the exercise is in that direction. This example is backward. Okay? So that is the one here. And this kind of combinations been seen a lot in controls. So I picked it to exercise.